Yeah.
Well, hello everybody, good morning, and welcome to this event organized by the Biotronics Laboratory and the program in Programa de Materiales Avanzados y Aplicaciones del Tecnológico de Costa Rica, así como por el LANOTEC, Laboratorio Nacional de Nanotecnología. Today we welcome Professor Fabio Cicoira. He's a professor of chemical engineering at Polytechnique of Montréal, and he received his master's in chemistry from the University of Bologna in Italy after a research internship at the European Laboratory for Particle Physics, CERN, and his PhD in material science and engineering from EPFL, Switzerland. He was a visiting scientist at Cornell University from 2007 to 2009 and a recipient of the prestigious Marie Curie International Outgoing Fellowship of the European Union. And he is well known for his studies of organic bioelectronics, self-healing materials, flexible and stretchable wearable electronics. Please welcome Professor Cicoira.
Thank you very much, Fabio, for this introduction, especially for this invitation. So it's a pleasure to be here and talk about my research. So you see here the title of the site here was stretchable something about electronics for electronics. And I will talk about different things. Most of my work is now centered on how to make materials visionary and used for electronic analysis. So that's, of course, whatever we speak of this, my group of humans we've changed a little bit, and the system is good to give you an idea where whatever is here, so it's working more than the US. And this is visually show when they go to the process with a nice weather, and our winter, and this is the view of our school. So for Montréal, it's like this school is engineering school, and it's affiliated to the University of Montréal, which is all districts. Okay, so as I said, most of my work comes in certain periods. About 1 year ago, we published a review about these materials, and we tried to explain that this certain ability is important for many applications. For instance, you can have remarkable electronics for several reasons, for electronic conceived, but also for everything which is really dependent on gas, convention, and also for wearable electronics. And of course, there are many different kinds of circuitry. You can have what is called autonomic or autonomic. This means that as soon as the material is damaged, the material can be stored electronics. Then sometimes you need to do something to trigger the process, which could be an liquid heating or heating. And in some other cases, you just have to stick material together. So there are many processes that we call all this circuitry. Why we want to do that? So the idea is that the future electronics needs to be flexible and stretchable for several reasons, for using wearables, for using environmental applications. Self-healable, because especially for environmental application, especially for the bulky device, you want to access the device each time you repair it. And also the idea is that these materials needs less flexible than themselves. And of course, we find this issue to measure because there are many organisms that are able to regenerate by themselves, like oxygen or octopus itself, if you see the short movie position. So, in electronics, certain properties would, of course, increase device longevity and also promote better integration with tissues. And when we started this research, there were very few materials with certain very few materials with electronic properties, which could be self-healing. And we were looking for a simple way to achieve healing without the complicated process.
Which material we use? Most of our work is made on conducting polymers. More in particular, we work with this material, which is polyethylene dioxythiophenene. Polyethylene dioxythiophenene, you see the structure here. So this is a thiophene, this is dioxy group. And this is doped with a polystyrene sulfonate. So very shortly, the idea of adding this polystyrene sulfonate is to dope the material to make it conductive. Why we work with this material? Because it's commercially available, and it has several advantages. We can, by processing it in different ways, we can achieve quite high conductivity. We can make films which can be operated in water, and we can tune the properties of the films. Then another important point of this is in general true for conducting polymers, is that they can be processed in different ways. So we can spin coat, spin cast, print, electrodeposit, electrospinning. So there are many ways to process these materials, which would give you different properties. Then, of course, we have challenges to achieve materials which could be used for real applications. For instance, the mechanical properties of these materials are, in general, poor. So we need to find a way to improve them. And then we also need to increase the chemical stability and find a way to pattern these materials to make devices. Then, as I said, there are several reasons to work with these materials. First of all is that we can operate any device made of this material in aqueous environment without any problems for the electronics. Then again, we can use different processing techniques. We can tune the properties of the materials. So, for instance, one of the advantages of the commercial PDOT is that it comes in an aqueous solution. So this means that it can be mixed with other water-soluble materials to make materials with much better mechanical properties. Then we don't have problems of corrosion or formation of passivation layers at the interface, which is a big advantage for application in bioelectronics. And another advantage is the fact that these materials can combine ionic and electronic transport. So this would mean that when we apply this material at some living interface, we will have a much lower impedance, so much better signal that we can acquire. So what we have done in the last years, we try to mix these materials with other polymers to make a structure which could be flexible, stretchable, and self-healable. The way we started with just, at some point, we thought that we could achieve self-healing materials by using simply, films of PDOT-PSS. Here is just the first experiment we did for self-healing. So you see, there is a conductive PDOT-PSS film, conducting polymer film, which connects an electrical circuit where there is a LED bulb. And of course, if you cut the material, there is no current flowing, so the circuit will be open. Then if you drop water on the damaged part, you can restore the electrical functionality, as you can see also from this quantitative plot here. So this is the current. Before cutting, you cut, there is no current, you add the water, the current comes back. So this shows you that this material can be self-healed by water. And the confirmation is that when we looked at the damage and healed area with SEM, we saw actually that after cut, the area is damaged, then after healing, the material goes back to the damaged area and restores the functionalities. Other interesting thing is that this process can be repeated in the same film. You can cut several times and you can still have the healing effect, and also that the process takes place in very short time, so within less than 1 second, which is a difference with respect to materials which take time to heal. Concerning the mechanism, we are still trying to understand exactly what happens. This is a little bit a speculation. So what we believe is that once we cut the materials, of course, they are separated, but there are some groups in the two parts that are separated which could form hydrogen bonding. And also we know that these materials can swell if they are put in contact with the water. So we believe that the reason why we can achieve this self-healing is a combination of swelling and formation of hydrogen bonding when these two parts come into contact. But there is still a lot of work needed to figure out what happens. Then, of course, we looked at different combinations of materials. So that's just maybe a little bit too complicated to show, but we tried to change the formulation of the conducting polymer, and then we saw that in some conditions we observe this healing, in some conditions we don't. And what we believe is that to observe this healing, we need some of the dopant inside, some of the polystyrene sulfonate, which gives the material these swelling properties. Now, next step was, okay, we can achieve self-healing in these films, but it's a little bit difficult to use these films because they cannot be handled easily. And also we want to see if by blending with other materials, we can achieve more interesting healing properties. So achieve healing that doesn't need any intervention from outside. So we know that there is a very rich chemistry of mixing of PDOT with other materials to achieve particular properties. So we mix with some chemicals to increase the conductivity, with some others to increase the mechanical properties, with some others to increase the substrates. And also there is a literature about the effect of some other, like surfactant molecules on the effect on the mechanical properties of this material. So our next step was to try to add polyethylene glycol, which is known as a plasticizer, in the sense that if we add these materials to other polymer, the effect is to decrease the Young modulus, so let's say increase the softness of the material. So again, we repeated the same experiment. In this case, it's very similar setup. The only difference is that now when we cut the material, we don't see any effect on the current. So you see that it's like there is no effect of the blade passing to the material. So this means that material heals as soon as you cut. And you can see it on this image here. That's high resolution time versus current measurement. And you can see that within less than 500 milliseconds, let's say, the damage is repaired. And actually this happens in very short time. That's just different kind of plot that shows you that you see the effect of the damage for a very short time, and then the properties are restored. Then we did some thermal analysis, and this was just to confirm that the polyethylene glycol still remains in the film after the processing. So it plays a role in this new self-healing properties. This is a kind of, let's say, live experiments. It's just the inverted microscope. Here we are showing how the film is cut, and you see that this is the effect of the blade on the film. What you can see already here is that you see that this space here is larger than here. So this means that the material starts to repair as soon as it is cut. Then, okay, we finished the cut. Then we went back on the area on the other side. And you can see that you can only observe the cut in some very short region. Otherwise, you cannot see any trace of the cut. So this tells you again that the material repairs as soon as it is damaged. Okay, so this was another step. Next step was to move with things that we can actually use to make devices which can be more easily handled. So the idea was to move towards self-healing hydrogels. So what we did in this case, we took a system which is already used, like the system polyvinyl alcohol borax, which is used to make hydrogels, and we added the conductive polymers. So you can see here that we can make gels that we can model in several shapes that we can also place on the skin, which is interesting for us because finally we want to use these materials to make electrodes. And also the mechanical properties are very interesting. You can make very small object and you can elongate it. Of course, it does not come back to the original shape, but there is this interesting plastic deformation. Then in this case, okay, we try to characterize the mechanical properties. Here you see the compressed stress versus strain. And you can see that if you introduce, this is just a simple hydrogel. If you introduce the conducting polymer, you get softer material, which is interesting because it means that this conductive material not only gives you higher conductivity, but also, for some reasons, gives you a softer material. And also on the and this is the Young modulus. So you see there is a decrease of Young modulus by introducing the conducting polymer, which means you have a softer material. This is the addition, and it's the same effect. You can see that if you add the conducting polymer, you have a material which has stronger addition on this case in animal skin, which again is something very interesting if we want to make electrodes which are applied directly on the skin. Self-healing properties. So in this case, this is the so-called cut and stick process. In the left side, you see two pieces of hydrogel. They were just cut, and you are not able to stick them to each other. Then this is the hydrogel obtained with conducting polymer. And here you can see that, excuse me. Yeah, in this case, you will see that if you stick the two pieces together, they will stay together. So you are able to achieve the cut and stick healing in this case. So you can cut the material, then you can put the material together. The same thing happens if you start for two pieces of material which are prepared separately. You can stick them and obtain a single piece of material. Then, as I said, the idea was to use this material for real devices. And what we made several types of electrodes. This is an example of electrodes for electrocardiogram, which have been tested directly in our lab on the volunteers. And you can see here, these are the characteristics obtained by our electrodes, and we compare them with several systems which are available on the market. What you can see here is that the characteristics are more or less the same. So our devices are as good as the commercial ones. The difference is that in our device, we can make all the components with one single material. So the hydrogel, in this case, acts as adhesive, as ionic conductor to transmit the signal between our body and the electrical circuit, and also as an electrical conductor. Usually in commercial electrodes, you have different components to have these functions. Of course, now we don't know if this will all someday become competitive with the existing processes, but at least we show that we can use this material for real devices. Then, of course, what we wanted to do, again, we wanted to improve further the properties of these materials. We want to have materials which could be processed both in form of thick gel and thin films. And in this case, we studied this system. So it's again, the conducting polymer. In this case, the other components of the gel are ethylene glycol and tannic acid. Tannic acid is a natural compound which occurs in many plants. And the characteristic of this material is that it has a lot of these OH groups, which are expected to favor addition by formation of hydrogen bondings. So even in this case, we could make freestanding films with these formulations that could be also used on the skin. And the interesting thing is that these films could also be printed, which is again an advantage for if we want to make real devices. So here again, you can see an effect of blending the material, the conducting polymer with other materials. In particular, here you see the effect of adding the tannic acid to the formulation of pilot and ethylene glycol. So you see here that even the tannic acid allows you to obtain a softer material. And you can see here that this stress strain. So this means that if you add more tannic acid, you can stretch the material more before it breaks. So you can go beyond 100% stretching. And again, you decrease the Young modulus at the same time. So again, you can obtain softer material which can be stretched more. And what is interesting here is that this material can exhibit different types of self-healing. We can have self-healing by cutting the material. So in this case, you just cut the material, you wait, and you obtain the recovery of electrical properties after the cut. And I believe also this is shown by a video here, which again shows the dynamic character of this material. So again, you cut, you just wait some time. Maybe in this case, the process is not as fast as the one I've shown you before, but you can see that if you wait a few seconds, the gap will close. So you won't observe any gap in between the two parts of the material. So in this case, the healing time is about 1 minute, 45 seconds. But again, it can be interesting for several applications to have a material which does not heal very fast. if I accelerate, you see that we see at the end you won't see any gap in between. Also, as I said before, you can achieve this cut and stick healing, so you can cut the material, you can overlap the two parts, and again observe the electrical self-healing. What is even interesting in this case that we were able to also achieve some mechanical healing. So what we did in this case, we took some. So this is the mechanical. These are the mechanical characteristic of a film that we made. Then we cut the film in two parts. We overlapped the two parts. And we measured again the stress-strain properties. And you can see that they're very similar to that of the pristine films. So in this case, we also achieved mechanical healing besides achieving the electrical one. Then again, this is just to show that this kind of characteristics can be obtained in several materials. This is just something we published recently. It's again another system. And again, here this is a mixture of polyurethaneol and PSS. Even in this case, you obtain similar characteristics. So you can, again, cut the material, wait some time, and observe the recovery. And of course, the reason why we made this material is also because it's easy to print, and we could print epidermal electrodes with this technique that give results similar to the ones I've already shown. So that's a little bit the process to print electrodes. So we make an aqueous dispersion of this material. So in this case, it's just PEDOT and polyurethaneol. Then we first print the silver pattern for the electrode, then we print the PEDOT on it, and then these electrodes are in principle ready for measurements. Yeah, of course. Yeah, we can also make the remaining part of the device, and then we can obtain any kind of signals. So with many of these formulations, we can make devices which actually work for real measurements. Now, the last idea we had in the group is to make something that we could also reuse, which is not only self-healing, but also reusable. And of course, I'm not going to explain why this is important. And the idea was to focus on polyurethane chemistry, which is very well known. It's very rich chemistry because you can achieve polyurethanes with several different properties in terms of mechanical strength, in terms of chemical stability, etc. Of course, there is still the issue that polyurethanes are made by isocyanate, which is a highly toxic chemical. So the idea is also to have isocyanate-free polyurethane. But our idea, at least, was since these materials are here already, and there are a lot of polyurethane around, so the idea is if we can reuse them before going to the recycling stage. So as I said, the chemistry can be very rich. So in the structure of polyurethane, we can add functionalities able to establish different kind of bonds, which could favor self-healing and also recyclability process. So in our case, we synthesize in a quite new kind of polyurethane in the lab. That's the synthesis. I won't go into the details. So that's everything okay? Yeah. Yeah. So you can see here the synthesis. So we always need to start with a diol for the synthesis and a structure which contains the isocyanate. That's a kind of general rule. In our case, so we got to the prepolymer, then we added this chain extender in the attempt to increase the flexibility and other mechanical properties of the material. Yeah, okay, so that's the synthesis part. Then we made our films. This is just the procedure of the film. And also in this case, we added some material which would further increase the softness of the material. In this case, our idea was to add the polyethylene glycol. Actually, the story why we added the polyethylene glycol is quite long, but I won't go to the details now. Anyway, what we get here, if we go to measure the stress-strain properties, you have some materials which are here on this side, which have quite low elongation at break. Then if you have the polyethylene glycol, what you get is that you can achieve up to 350% strain. So this means you can apply 350% strain before the material breaks. And the other interesting thing is that you have a quite large region where the material behaves elastically. So you hear elastically means that the stress-strain relation is linear, and this happens up to 30%. And then you have a region of plastic deformation. And these are the elongational break and the Young modulus. And what is interesting, for instance, for this material, that if you take the Young modulus in the linear region and elongational break, they are also, both of them, much larger than that of the pristine materials. Okay, so we have a stretchability. We have a material which is rigid in a certain range. This is just cycling studies to show that material is stable. And these are the variation of electrical properties upon stretching. So you can see here that you start from, this is just the ratio between the initial resistance and the resistance you get after a certain elongation. You can see that after a certain elongation, the resistance starts to increase. So this means that the material is less conductive if you stretch it, which is this almost always happens. But you can see that the material is still conductive, even if it is stretched. Self-healing experiment, so we repeated again the same thing. So we tried the autonomous healing. In this case, we also tried to see if the material could recover scratches on the surface by healing, and we tried also the cut and stick healing. So these are the results. So if we just take the simple material, there is no recovery after cut, but if you cut the material containing the polyurethane and the polyethylene glycol, you observe the autonomic self-healing that we have already observed. Mechanical healing, so in this case, we also repeat the experiment. We took a material, we cut the material, we stick them together, and we observe again that we can recover the mechanical properties. The only difference is that in this case, we need moderate heating to recover the properties. Scratch, again, so if we take a pristine conducting polymer film, we scratch it, we try to recover the properties by heating, nothing happens. If we have the polyurethane and polyethylene glycol, you can see that you can scratch the material at the surface. The scratch is quite deep, it's about 200 nanometers. And then you can see if you heat at about 50 degrees for 10 minutes, then the scratch disappears. So we can recover the scratch at the surface. Last thing, is it possible to recycle these materials? So what we did, this was intended for the mechanical properties. We made these dog bone samples, which are used to measure the mechanical properties of the materials. We cut them in small pieces, and then we put them in the hot press, and we tried to make the same shape. And this is just to show that we can reshape the material in any shape. Dolphin is just arbitrary shape that can be anything. So what we observe here is that you can see the properties of mechanical properties of the pristine films and the film which has been recycled once and 10 times, and you can see that there is not a big change in the mechanical properties after this process. Same things for electrical properties. You can take the material, destroy it, reshape it, you get essentially the same electrical properties, and I think this is very promising for the recyclability of material. This is just last experiment we did. The idea was just to, is it possible to use this material to make a device that then could be reused? So we made a very simple pressure sensor based on this material. And what we did, we used it, then we destroyed, we reshaped a few times, and up to, after recycling, it still works. So it shows that it's possible to make devices with these materials and then have them reusable. Okay, that was the part about self-healing. Then now, if there is time, I don't know if I can continue, I can show some work about other kind of devices. So electrochemical transistors. And the idea here was to make, again, devices which could be stretchable. And we found different ways to do it. So what happens when we have a material, a conducting polymer, and we apply some strain, you will create cracks. But what we found out a few years ago is that the density of these cracks can be tuned by changing some parameters. So for instance, if you have a thicker film, it's easier to damage them. If you use a drying temperature, which is very high, it's easier to damage them. So we found out that it's possible to reduce the damage by heating at different temperatures. Then another approach to make stretchable devices to use electrospinning. This I will just show this very quickly. In principle, what I want to show here is that if you process a material as simple thin film, you obtain a certain stretchability. If you process by electrospinning, you have a device which is made of fibers. And of course, when you elongate devices, not all the fibers will break. Some of them will survive. And you can achieve devices with a quite important stretchability, up to 100%. So you can have transistors that still work after you stretch them. Last part about devices is about printed organic transistors, conducting polymer transistors. So we can use the printer to make both the electrical contacts and the channel. So you know that to make a transistor, you need to have the electrode, source and drain, then you have to have the channel and also the third electrode at the gate. So we could print all these devices and we can achieve quite stable electronic characteristics. What we can do more, we can also print the dielectric layer. So just a few words about this. These transistors are called electrochemical transistors. So the way they are made, it's that here you have two electrodes, source and drain between, so you have source and drain, and in between source and drain, you have the channel, which is again a conducting polymer in this case. Then you have the third electrode, which is the gate, and then you have an electrolyte, which provides the current modulation. So what we are showing here is that we can print all the components, including the electrolyte, which in this case is a kind of ionically conductive hydrogel. And here is just to show you that we can make devices which work pretty well. So you see, this is the difference between these two currents is called on-off ratio, and in our case it's about 1,000, so it's relatively high. And depending on the hydrogel, we can achieve devices which could work for several days. So about 2 months, these devices are stable if measured every day. And these devices can also be stretchable. So you can see here that up to 60%, you observe very little change in these electronic characteristics, depending if you stretch in the two directions. So of course, if you stretch along the length, you can stretch up to a certain point. If you stretch along the width, you have another reaction of the devices. Okay, so last part about, it's about bioelectronic devices. So it's about our work on invasive devices for bioelectronics. In this case, what we do, we take devices which are made by metals because they need to penetrate into the tissues, for instance, in the skin or in the brain, and we modify their properties by using coatings of conducting polymers. Yeah, why we want to do that? Because if we have a metal which is inserted in the tissue, we have several foreign body reactions. Because due to the difference in Young modulus between the metal and the tissue, and also we can have a degradation of electronic properties over time of the metal because formation of tissue around the electrode and also corrosion and other reactions that could take place in the living environment. And of course, we have also spatial resolution limitation. When we make electrodes very small, then the impedance would increase, which would make it difficult to acquire a clean signal. So in this case, the approach is always the same. The electrodes, the type of electrode might change, but what we do, we take a metallic electrode, which could be stainless steel, platinum, or iridium, or any other metal. We coat the active part of the metal by using electrodeposition of conducting polymers, and then we observe how the devices behave for real measurements. That's just the way we perform the electrodeposition. So, as I said before, these conducting polymers can be also electropolymerized in situ. In this case, you start with the monomer, which is just the monomer of the EDOT. You use a salt supporting electrolyte for the process, which could act as dopant at the end. And you can choose different solvents for the polymerization. So the configuration would be that this is an electrochemical cell. The working electrode would be the electrode you want to cover with material. Then the reference and counter are electrodes which are typically used for this measurement. So silver chloride, or platinum counter electrode. The first thing we do in this kind of electrodes, and we measure the impedance in the physiological solution. And what you observe is that if you take, in this case, a stainless steel electrode, pretty large electrode, if you look at the impedance difference between the uncoated and coated material, we have a decrease of 3 orders of magnitude. So this tells you that just by coating stainless steel with the conducting polymer, we can decrease the impedance of the material. This is cyclic voltammetry. Again, this is the cyclic voltammetry of the bare metal that you cannot really see here because of the scale. But this tells you that once you have a conducting polymer coating, it's much easier to store charge into the material, which could be an advantage, for instance, when you want to deliver electrical stimulation. Then, of course, once we make these electrodes, since they have to be implanted in tissue, we made some stability tests. So we tried aging in solution, autoclaving, sterilization, and we found out that here you can see that there is very small changes of the properties upon these treatments. Then we implanted the electrode, in this case in the muscles of mice. And what I want to show here is that if you look at the signal-to-noise ratio between the two systems, you can see that you can clearly decrease the signal-to-noise ratio if you have coated electrodes, which is also visible in this case. So you see here, these are the bare electrodes, these are the coated electrodes. You can see here that they're much more effective in detecting signals. So this was, the other point is that we measured the impedance after 6 weeks after the implantation of the devices, and you can see that even after so long time, there is no change in the impedance the impedance of the coated electrode is still much lower than that of the uncoated ones. Very last thing, so the previous work was on muscles, so we do also work with the electrodes to be implanted in the brain. This is one of the last work we did. It's similar approach. We want to see what happens if we implant these electrodes in the brain for a long time. In this case, we used a higher number of animals to have more statistical significance. And that's more or less the way we perform the experiment. So we perform the surgery, then we wait for a few days, and then we measure for 2 months to see if there is any issue with the implants over time. So these are the measurements of, again, these are impedances of bare electrode, and after 2 months, the comparison. And you can see that if you look at the values at low frequency, because this is the frequency that are used in usually for all biomedical stimulations, about 1 kilohertz, we see that even after 2 months, we still have lower impedances in coated electrodes. Yeah, here you can see, that's maybe the most interesting data here. You see the impedance at 1 kilohertz in vivo, day by day, 2 months after the surgery. So these are the days after surgery. We just measure the impedance. It's 1 week during which we don't deliver any stimulation. Then what is interesting is that after the first stimulation, the impedances of the two electrodes decrease. This is probably because when you apply the first pulse, the electrodes clean up in some way. So you observe a decrease of impedance in both systems. But then over time, the impedances of the two electrodes, so the impedance of the electrodes which are coated with conducting polymer, they stay much lower compared to that which are uncoated. Then we observe the failure here. One electrode just stopped working. In this case, we had an increase. But if we exclude this electrode from the count, we still have consistent decrease of impedance. Okay. Then, in this case, what you do, you observe the tissue around the electrode to see if you see any evidence of damage of the tissue. In this case, we could not say much because if we look at the metal electrodes or conducting polymer electrodes, the tissue around the electrode looks essentially the same. So at least we could say that there is no additional damage induced by the polymer with respect to electrodes in platinum iridium, which are currently used for this application. So at least our electrodes, they do not produce more damage than, let's say, the currently used ones. Okay, that just to say that sometimes we tried also some applications beyond science. We try to work with the artists to see if we can use this device to detect some emotion. So this is a measurement of EDA, which also many smartwatches have. It's just electrodermal activity. So it's measured the response of your skin to external stimuli, which could be sometimes induced by stress or other factors. It's not very scientific or medical measurement, but it has some, let's say, some value. And in this case, what we did, we used devices which are made by some performing artists to monitor the reaction of the public or themselves during shows. And we just showed that some measurements could be obtained also by using our devices, which are much easier to wear compared to more conventional ones. I think with this I finished. So the messages is that, messages are here. So we can make real devices with organic materials, which can be used for many different things. And then by processing the materials in different ways, we can have different kind of devices for several applications. Self-healing is a new opportunity for sustainable electronics. And then we have to do a lot of work to understand what really happens during this process. And we need to improve the shelf life of these materials for other applications. What is it? Okay. I think this is really the last slide. So, of course, I have to acknowledge the funding, which mostly come from public agencies. And I already thanked the group in the beginning, so I'm just waiting for your questions. Thank you very much.
Thank you very much, Professor. This is so impressive, such a great work in putting in contact all these devices that can be rebuilt and healed and also connected electrically with the tissues. So now we're gonna have a part open for questions from the students and from the audience. We also had about 40 people that were connected online, and thank you very much for everybody who is watching. I saw some old friends from the University of California in Riverside, also students, colleagues that graduated with me from the material science here at Tech. So hello, everybody. So do you guys have any questions for the professor? First.
I have a question about self-helber. Is a specific temperature on a specific condition for the material can self-helper, or what something?
So if the self-healing needs some certain temperature, the answer is that with the system using polyurethane, we need moderate heating at about 50 degrees to achieve the heating. It might be that it happens if we wait a long time. This we don't know yet. For the other system, everything happens at room temperature. We don't have to do anything. So the fact to need some heating could be an advantage in some cases when you want to have the event triggered by something. And it's practical to have a heat to trigger the event because heating can be applied remotely, so it could be useful for some other applications.
So I have a question because I noticed that in some of your data for the impedance of the electrons in the brain, with time, the impedance was lower, no? In some of the graph. Can you go back to the...
This one?
The one from before? Yes, in this one, the value after 2 months, it looks like slightly lower.
Yeah, there are several things that we don't understand yet. So for instance, here we find that for the bare electrodes, the impedance is a bit lower after implantation. Why this happens is still unclear, because there are several processes that can take place into the tissue. Is very complicated environment. So what we can see here is that even after 2 months, the coating reduces the impedance. Then, of course, there is some variation, and this still is something that we cannot understand. So you can see the difference here. Again, this tells you that for the bare electrodes, you can have some decrease. Why? It's unclear, but what you can see, this distribution is quite broad. It means that you cannot really control the impedance if you don't have the coating. If you have the coating, it's a bit easier to control. But of course, there are many things that needs to be understood for this particular application.
So you coat the tip of the syringe or the needle, the tip of the needle, it is like a needle with the polymer. So when you put the needle inside the skin or inside the tissue, the polymer doesn't move back?
No. So that's just an example. So in this case, it's just, this is the electrode used for electromyography. It's quite thick, twisted wire, so that's pretty big. And in this case, this brain electrode, it's only this small part here which is exposed. No, when you insert, of course, the reason why we could say, no, the polymer is still there, it's because we still see this difference in impedance between the coated and uncoated one. And what we also do when we extract the electrode at the end, we look at the electrode to see if the polymer is still there. And again, what I can see here, for instance, here we clearly observe a failure in the system. We saw the impedance increasing. So what we did, we noticed that one of the electrodes after we extracted them didn't have the coating. 1 out of 5. So there are still some possibility of failure. How to control? Of course, we can increase the adhesion and so on, but there are still things that cannot be fully predicted. But again, it means 1 out of 5 means 80% of the electrodes, they retain their properties when implanted. So.
And also, I have a question about the materials that are cut and then go back together.
Yeah.
So do you think that, what is the electron transfer mechanism in that material? Because there are no polymer chains, or do you think the polymer chains are rebuilt, like the covalent bonds are formed again? Or?
You know, how this happens, it's still under investigation. Of course, if you observe the conductivity again, means that the bonds the interactions are somehow reestablished. You know, probably by hydrogen bond, van der Waals interactions, but if you see that the properties remain intact, so it means that the conduction path that you have impeded before the damage can be reestablished. The mechanism is most likely hopping, because it's thermally activated hopping, because it's whole conductor with not very high conductivity, so still thermal hopping of charges. Yeah.
Does anybody else have another question from the audience? No? So now I will just, no? Okay, there is one question. Okay, so we have one question from Engineer Oldemar Delgado. These materials, do they have some benefits during laser making process being used in the automotive industry processes?
Like this, I really have no idea. So laser processing?
Laser processing for automotive industry. Mhm.
No, the only place I could see these materials in automotive would be to make electrochromic windows.
Mhm.
But I don't think that, because they are already used in airplanes, right? But I do not think that polymers are competitive with respect to inorganic oxides and other things. So I have no idea on which could be the applications to automotive industry of this. Maybe if the question can be reformulated, I can discuss that. And laser processing, I don't know much about laser processing of these materials.
Okay, well, thank you very much for everybody joining, and I am so glad to have the professor here. Let's give him another applause and for hoping that he enjoys his visit here in Costa Rica.